We now want to derive a very, very important result between the RMS speed of a molecule in a gas and its connection to temperature. Okay, so to start, suppose you have a molecule in a container, okay, and it has mass m. And initially suppose that it's just moving in the x direction with velocity vx sub I. And it hits the side of the container and bounces off in an elastic collision with a velocity vxf. Now in our coordinate system, okay, the initial velocity is positive, plus x is to the right, and the final velocity is negative, okay? But if the collision is truly elastic, then the final speed is going to equal the initial speed to within absolute value signs, right? So their magnitudes are going to be equal, all right? Now, so the entire question is, what force does the molecule exert on the side of the container? Okay. And what we're going to do is we're going to look at the average force. So, of course, the maximum force that the container exerts on the molecule is going to be during the collision itself, right? But if we're just concerned with the change in momentum of the molecule itself, if we're concerned with the change in momentum on average, okay, so in other words, if we just let this molecule loose in the container and let it bounce back and forth, what is the long-term average force that it will exert on the side of the container? Okay, so of course the force is equal to the change in momentum, and here P is momentum, not pressure. Okay, change in momentum over change in time. But if my momentum is equal to mv, right, P is equal to mv, then delta P is equal to final momentum. Let me draw that a little bit better. Then this is going to be final momentum minus the initial momentum, which is going to be negative mvxf minus mvx sub I. And that's over the time interval. Now, again, the time, if we're concerned with the average force, this is not going to be just the time that the molecule is in contact with the wall, but again, over several cycles of the molecule bouncing back and forth, okay? So if we look at the average force that the wall exerts on the molecule over an extended period of time, then we can think of this as a cyclic process where the molecule hits this wall and then it'll come over and hit this wall, and then the cycle just continues, okay? So the average force that the wall exerts on the particle, if my container has length L, okay, then the speed Vx, now I'm dropping the x and the f and the I subscripts, the final and the initial subscripts, because this is an elastic collision. The velocity magnitude is not going to change, right? So we can drop the x and the I, or the not the x, but the f and the I subscripts with impunity here. And in doing that, first of all, the momentum itself becomes negative 2m Vx, and this is still divided by delta t. but Vx is going to be equal to 2L divided by the time that it takes to move between the wall and then back again. Okay, so the particle will start at this wall, hit this wall, and then come back again. And so it travels a total distance of twice the length of the container with some speed Vx. And therefore, the time interval is equal to 2L over Vx. So if I make that substitution into my equation, and I've dropped the minus sign from the change in momentum because the minus sign is really irrelevant. It's just an artifact of our coordinate system. We could have just as easily made to the left positive and to the right negative, and it really doesn't matter. Okay. And so 2L over Vx is my time. I'm dropping the minus sign, and I obtain this expression from those two steps, dropping the minus sign and then making this substitution. And then we get m times Vx squared divided by L. Okay? And so, this is the average force. Well, let me put it this way. This is the force that the wall will, on average, over several cycles, exert on the particle. Okay? But what happens now if we fill our container with particles? Right? What's the average force exerted by a total of n particles? Okay, so to do that, what we do is we say, okay, this now, and this is one of the reasons why I wanted to drop the I subscripts from earlier, but we're now going to say this is the ith particle. So I is an index now, not initial. So up here, I meant initial. And here it's an index. Okay. And so the ith force, or the force exerted on the ith particle, will be m Vx squared for that particle divided by the length of the container. And so then the total force is the sum of this across all of your particles. Whoops. We want to go I equals 1. So I is our index. We start with our first particle and go up to the total number of particles in the container. And so then this becomes mvx for the ith particle squared divided by L. Okay? But m and L are constant, so they can actually come out of the summation. And so now what we can do is we can use the definition of average. Okay? So in other words, this total force, you can then take, so this is the total force from all of the particles, and then you can say, okay, out of those particles, what is the average? right? And so then F average is going to be the what you're basically doing is going to multiply this by 1 in the form of n over n. Okay, and what happens here is that I have n times m over L, but then I'm going to group the 1 over n with the summation. Okay, because adding up all of the quantities of some number of things and then dividing it by that number of things is the average. So this is the average square of the speed of the entire set of molecules. Okay? So this is the average of the square of the speeds of all of your molecules. All right? So we can then write this like this. Okay? And now we generalize this to say, okay, but wait a minute. What about all of the different directions the molecules can be moving in the container? They're certainly not all moving in the x direction. They're going to collide with each other and they're going to change directions, and you're going to have z components and y components and so forth. And so we can use the general rule that the square, or the average of the square velocity, is equal to the sum of the averages of each component. Okay? And so there's another assumption that goes in here, and this assumption is the assumption of isotropy, or isotropy. So what this means is that if the particles are all uniform in makeup, right, so that all of the particles are the same type essentially, and there's no other factors influencing the gas in the container, then the speeds should be essentially evenly distributed. Okay? In other words, for at a given snapshot, you should see just as much average velocity in the x direction as you should in the y as you should in the z. And so what that means is that Vx, the average of the square of the velocity in the x direction, should equal the average of the square of the velocity in the y direction, which should equal the average of the square of the velocity in the z direction. Okay? So if that's the case, then the total average of the square should equal 3 times the average of the square in the x direction. Okay? So that's what isotropy means, that or if the system is isotropic, then your molecules or individual atoms, whatever the case may be, will all have smoothly and randomly oriented velocities such that essentially the components in each direction will be equal on average. Okay? And remember, okay, so yeah, in my little diagram here we have, maybe, 10, 15 atoms. In a true gas container, you're talking about Avogadro's number, on the order of Avogadro's number. And so when you have 10 to the 20 plus atoms in a container, again, neglecting any external influences, they should be completely randomized. The velocities will be nearly completely randomized, and if you measure the total velocity in the x direction, it will be equal to the total velocity in the y direction, which will be equal to the total velocity in the z direction. And by the way, in a truly isotropic gas, the total velocity vector of all of the sum of all of the molecules should be really close to zero, because you should have just as much in the negative x as you should in the positive x, just as much y in the negative y, just as much z as in the negative z. So you should average your velocities out to zero, but when you take the square, you really don't care about those negative directions. But you should still find that the squares of the averages, the averages of the squares should still all be the same in a truly isotropic system. Okay? So, what that means is, I said all of that to get to this punchline, that the average of Vx squared is equal to the total average squared, or the average of the total square, divided by 3. Okay? And so, if we plug that into our average force equation, okay, so let's kind of sum up where we are. Our average force is equal to N times M over L times Vx squared on average, right? But we just said that Vx squared average is equal to V squared average divided by 3. So now if we insert this, this is going to be NM, not Vx, but just V squared, averaged divided by 3 times L. Okay? And so now remember that pressure, and this is why I like to try and differentiate how I write my P's, because we already used lowercase p for momentum. But our pressure is equal to force divided by area. So my pressure can be thought of as N times M average. That shouldn't be a vector sign, that should just be an average sign. Well, let's write our squared first, since we're technically averaging the square, divided by 3LA. Okay? But L was the length of the container, but A is the area of the face we're interested in. Okay? So A times L is my volume. And therefore, P is equal to F. Let's do it this way. We already have it as F over A. N times M times the average of the squares divided by 3V. Okay? But we can now write this with the pressure hang on just a second. There we go. So PV is equal to NM square of our average divided by 3, right? And this is the left-hand side of the ideal gas law, right? This is the left-hand side of the ideal gas law. So this is going to be equal to NKBT. Now, look at this middle term here. The middle term contains mv squared. Okay, so this is related to the kinetic energy. Okay, mv squared is going to be related to your kinetic energy. Our ends cancel, the total number of molecules, it doesn't matter. Okay, and I can multiply both sides by 3. So m times the average of the square of your speeds is equal to 3 kBT. And so then to convert this into kinetic energy, multiply by 1/2 on both sides. Okay? So the left-hand side represents the average kinetic energy of a molecule in your gas. Okay? Therefore, by the equal sign, this is what must be the average kinetic energy of a molecule in your gas as well. But notice that this one is related to temperature. So the quotation marks are just kind of finishing that statement, right? Also the average kinetic energy of a molecule in the gas, but it's related to your temperature. So this equation puts temperature on sort of a firmer physical footing, right? Initially, we said temperature is something that you measure with a thermometer. That's not very enlightening. What are you measuring with that thermometer? Well, what you're measuring in one sense is related to the average kinetic energy of a molecule in your gas. So, if I claim that this is your average kinetic energy, then we can immediately state what temperature is. Okay, so one basic working definition of temperature is that it is 2/3 times the kinetic energy, average kinetic energy, divided by Boltzmann's constant for a container. Okay, a container with any gas. The temperature of that gas is going to be equal to 2/3 its kinetic energy of the average particle. Or I should say 2/3 of the average kinetic energy of the entire collection of particles, the entire ensemble, as they're sometimes called, divided by Boltzmann's constant. And now you can really see where the units of Boltzmann's constant come from, right? we didn't harp on this before, but if this side, if the left, or if the left side is joules, 3/2 doesn't get any units, but your Boltzmann's constant must have units, and T must have units of Kelvin, and so your Boltzmann's constant must have units of joules per Kelvin. Okay. We also will make a second kind of insight here. Okay. And that insight is that we're going to define a new kind of energy. Okay. And we're going to call it the internal energy. So the internal energy of a thermodynamic system is just the sum of all of the mechanical energies of all the molecules. Okay. I almost started to draw N here, but this needs to be 1. Okay. So, in a truly monatomic gas, and what we mean by monatomic is same type of atom, right? So you would only have oxygen or only have nitrogen, so on and so forth. Okay. If the if the kinetic energy of a single atom on average is equal to 3/2 kBt, then the total internal energy of the system, if there's only translational kinetic energy, okay? So there's no potential energy associated with these molecules as they're flying around in the container, in other words. Okay? So your kinetic energy, your average kinetic energy per molecule or particle is 3/2 kBt. Your total internal energy, E int, and maybe we'll write this like this. Okay. Is going to be, this sum is going to be equal to N times your average. Okay. And we can show that explicitly by making the substitution, or not necessarily making a substitution, but remember that Ke average is equal to 1 over N times the sum of I equals 1 to N of Ke for the ith particle. right? And so if that's the average, then the total would have to be n times that. Whoops. Again, not a vector sign. Okay. So then your in this case, if I multiply this through, my ends cancel out, and it's just the sum of KEI. But that's exactly what we're claiming right here, right? So your total internal energy is just n times the average, okay? But your average was also 3/2 kBT. So your total can be thought of as n times that. Okay? And this is most often written as 3/2 n times kb times t. And remember that this is the number of moles of your substance, and NaKB is the gas constant. So this can also be written as 3/2 nRT. Okay. And so, if you're working with the total number of molecules in Boltzmann's constant, then your total internal energy is given by this. And if you're working with moles in the gas constant, then it is given by this. And there's also another important result here, and that is this. If we come back here, the 1/2s go away. So what I'm going to do is I'm going to solve for V, okay? So your this velocity is what we call the RMS velocity. Okay? And RMS stands for root mean square. So in other words, it's the square root of the average of the square. But averaging the square is basically what we did the past two slides, right? So this velocity gives a measure Okay, or an atom, I really should say. In a gas. And for the moment, we're assuming that this is an ideal gas. Okay. Um, and so the whole point here, the take home message is that your average kinetic energy is equal to 3 halves kBt. This establishes a relationship between temp and kinetic energy. Okay, so temperature is a measure of the average kinetic energy of a particle in your gas. Okay, again, I said particle. You can substitute atom or molecule. Um, and that's perfectly a fine definition of temperature, and it puts it on a more physical footing than just saying it's something that we measure with a thermometer, right? Your average internal energy is n times this. Okay? So if you know how many particles are in your system and you know the average kinetic energy that they possess, then you know the total average internal energy. Or likewise, if you know what temperature the system is being held at and you know how many particles there are, then you can calculate the total internal energy. But because temperature is a macroscopically measurable thing, I can measure it with a thermometer, okay? Then this actually allows you to state what the average speed of a molecule in the gas is in some sort of meaningful units, right? If I know what the temperature is, then I can multiply that by Boltzmann's constant and then by 3 and then divide it by the mass of my particle or atom or molecule. Now, there's one thing to note. Oh, well, so these three equations are the major take-home portions of this lecture. Okay, these three equations are the punchlines. All right. Um, T for these equations to work for this entire lecture, everywhere that T appears in this lecture, T must be in Kelvin. Okay, and partially because Boltzmann's constant is joules per Kelvin, but more importantly, Kelvin is a truly physical temperature scale in that it is anchored at absolute zero. And if you put in other arbitrary temperature units in, if you were in, like, say, Celsius or Fahrenheit, then you would get extremely wonky results for this RMS calculation. Okay. But in any case, if you're in SI and you're using Kelvin and you can use joules per kilogram for Boltzmann's constant and then whatever the mass of your atom or particle is in kilograms, then you will get your speed in meters per second. Okay, so this will tell you if you know what kind of gas you have, and therefore you know M, and you can measure its temperature, then you can actually state what the average speed of an atom in your sample. You can state what the average speed of that atom is. Okay. So, some very important results here, but the big punchline is being able to connect temperature to something physical. In this case, the kinetic energy. Okay, so I hope that makes sense, and we will see you in the next lecture.